Good afternoon, everybody. Welcome to another exciting afternoon at Chem 170 Organic Chemistry with your host, me, Dr. White. And we got a fun day ahead of us. Can you believe our first week is almost over? Boy, this went fast. I hope it goes fast for you. All right, a couple announcements. I got them written right here. All right, don't forget, the lab I did yesterday is due next Monday. All labs are found and can be uploaded in the assignment area of D2L. Again, the lab we did yesterday, I talked about yesterday, is due next Monday. You need to upload it as a PDF file in the assignment area for that lab. I have two files, one's Word, the other's PDF. So if you can't open Word files, any device can usually open up a PDF file. And that will show you, if you don't have a scanner, how to use a cell phone, or as some people call a smartphone. Anybody ever see a dumb phone? Well, I guess the old phones were, but anyways, how to take pictures of whatever you're writing and your labs, and also be your test too, and convert it into a PDF file and then upload it. That's pretty simple. Students have been doing it now over a year since the pandemic, when I found I better figure out how to show students how to do that, because not all my students have scanners. I actually have two scanners. One you can't see, and when I just bought this new printer, my old one, well, it was old and needed to be replaced, has both a printer and a scanner and a fax machine. Does anybody do faxes anymore? Anyways, that's one thing. Now, another announcement I want to make is this Monday, I will go after class, and it's optional. I will go teach anybody who wants to stick around how to eliminate test anxiety. And over the years, it's been a serious problem for some students where they know how to do it. They sit down, take a test, and all of a sudden their brain goes, and this method works beautifully. It's easy to learn. It takes me about under 10 minutes to teach it, and you've got to practice it like anything else you have to master. And over the years, F, D, and C students have become B and A students with this. Plus, you can use it in your other classes. Now, I will not keep it in the video. I'll cut that out, but that will be Monday. And finally, one last thing. I was talking to one of your colleagues yesterday, and I thought I'd talk about it now is, I think a lot of you are in a major path, or your major, where you probably need to get into some school or program, a letter of recommendation. And if you're in nursing or planning on being a nurse, nurses and most doctors do not like organic chemistry, because mainly I didn't teach it to them, but it's been taught really bad by a lot of schools. They hate it. And when they see a letter of recommendation from an organic chemistry instructor, they go, wow, this person must be good. I do write letters of recommendation. Most of the major schools in the Chicagoland, even the Midwest, know me, because I always send them my best students. And I have how should I say, criteria. You get a high B or an A in my class. And now, since we're online, if I get to meet you, say either my office hours or after class, I get to know you a little bit. And also, which usually hasn't happened except once, you haven't made me mad at you, upset, ticked me off, I will write a letter of recommendation. And my letter of recommendations work real good. In fact, a couple of schools, UIC, nursing, and also Elmhurst, they've emailed me back and saying, can you send us more students? So that's something to remember, to get a good grade, and also during the semester, try and meet me so I get to meet you. All right, before I start, any questions from anybody? All right, well, in that case, I promised I'd go through the practice problems, and I will. Now, one thing I should say is that even though I don't have my hearing aids on because I have amplified speakers up there, letters of the alphabet are hard for me to make out sometimes. So if they ask you once or twice if you want which letter, please be patient. That's my problem, not yours. All right, there we go. All right, one thing, the way I do this is I'll go through one page at a time. And if you have any, I'll do one or two from each page. And if you have any questions, ask. You want me to do a certain problem, ask. Because remember, in my class, there's no such thing as a dumb question. All right, so the first skill in the Alkanes practice problem set, I hope you'll all try this on your own. Remember, just like I talked about the first day, you don't know how to ride a bike and you watch the Blu-ray how to ride a bike. First time you get on a bike, you'll fall off. Well, watching me do it is like watching the Blu-ray. You don't want to fall off on the test. All right, first one, how many carbons are in the longest chain? Remember, carbons bond together are considered connect together part of a chain. And if we look at C, we have across 5. We go here 1, 2, 3, 4, and here 1, 2, 3, 4, and the longest chain is 5. Now, here you go 2 ways, and each way you get 6. There's another chain, 1, 2, 3, 4, 5, but the longest chain is 6. Now, if you look at E, and I think this problem set, I'll probably do a few more. But anyways, E, the longest chain doesn't have to be across. If you have 1, 2, 3, 4, 5 across, but if I go 1, 2, 3, 4, 5, 6, 7, it's the longest chain. And you could have started with this carbon here as 1 also, and you still get 7. If you notice F, I really went all out. If you go across 1, 2, 3, 4, 5, 6, but if you go 1, 2, 3, 4, 5, 6, 7, 8, 9, that's the longest chain. Now, once you know how to do the longest chain, we can now talk about Iupac names. Remember, I'll never ask on a test, what does Iupac stand for? Even though I think it's cool to say it stands for the International Union of Pure Applied Chemistry. But when you see the acronym Iupac, ooh, big word there, acronym. Anyways, Iupac, that means the official name. And here to give the Iupac name for the following. And here you find the longest chain. And if there's no branching, then you use the table right here. And hopefully you've learned these. Hint, hopefully you've learned these. Double hint, hopefully you've really learned these. And actually that was a triple hint. No methane, 1 carbon, ethane 2, propane 3, octane 8, and so on to decane 10. It actually goes higher, like undecane is 11, dodecane 12, and so on. But usually after 10, you start using a lot of common names, which I'll teach you also. So if we go back to the problem set, three carbons. Oh, it's your old friend propane. 6 carbons, 1, 2, 3, 4, 5, 6 is hexane. Now you can use parentheses. I won't on a test. You can use either way if it gets too long and you don't want to write them all. But I'd stay away from that. It's one less mistake to make. Now, if we look at D, what's the longest chain? There are 2 ways of counting it. It's 4. And that's butane. Now we have something left over. and that's branched to alkyl group, and one carbon is methyl, and hopefully you've learned this chart, which both of these files, the one with the alkane names and the alkyl groups, are in the lecture folder of D2L for you to download and either write or print so you can study from it. One carbon alkyl group is methyl, 2 ethyl, 3 to the end carbon is N-propyl, 3 to the center carbon is isopropyl, and then 4 carbons to the end carbon is N-butyl. 1 carbon with 3 carbons attached to it, that center carbon is attached to a ring or a chain. That's a tert-butyl, or starting next week, I'm gonna get lazy because I'm a lazy organic chemist. We all are organic chemists, that is our lazy. It's T-butyl. So 1 carbon methyl, and then you have to find what carbon it is. Remember, for acyclic compounds, alkanes, where you don't have a ring, you start from the end of the chain. You go here, 1, 2, you go here, 1, 2, 3, use the lower number, it's 2, so it's 2-methylbutane. Now, E is the same thing. I just wanted to show you all I've done from D to E is rotated 180 degrees. Now, if we look at G, the first thing you have to do is find the longest chain. And I made it easy for you in this one. It's 1, 2, 3, 4, 5, 6, 7, 8, 9. That's no name. Once you have that, you have left over here a methyl group, 3 carbons, center carbon, alkyl group, isopropyl. And notice you start from this end to get the lower numbers for all the alkyl groups. Methyl's on 2, isopropyl is on 4. So this would be 2-methyl, 4-isopropyl, no name. However, since I'm not holding you to the alphabet rule, I hold myself to it, but I won't hold you to it on a test. If you put down 4-isopropyl, 2-methyl, no name, that would be correct. Now we have a ring. Ooh, and how do you do a ring? You don't show carbons on a ring. Use the line method, that's what this is called. And you count every bend in the line as a carbon. 1, 2, 3, 4, 5, 6. And then you name that as an alkane, 6 carbons, hexane. But because it's a ring, we put in front cyclohexane. Hey, you know something? I'm gonna share. What would be the name of that compound? 3 points each. In other words, give the Iupac name for the following. That's your turn. And since all of you have your webcam turned off, don't forget to use the emoji to let me know when you're done, because I can't see when you're done. I think everybody's done. And how do you do that? You count the bends in a line. 1, 2, 3, 4, 5. And 5 is pentane, but it's a ring, so we used a prefix, cyclo. So the full name is cyclopentane. Now, common mistake on test number 1, if I were to write this problem, students forget to put the cyclo. Don't. It's wrong. Pentane and cyclopentane. Pentane is this compound. Pentane is acyclic, not in a ring. The cyclo tells you you have a ring and you need to put that there. So make sure you do that, because over the years, I've seen students lose a lot of points when they forget to do the whole name. Now, when you have an alkyl group on a ring, and only one, wherever it is on the ring, it's always going to be carbon 1, because the alkyl groups get the lowest number when you're numbering them, whether a ring or whatever. Well, everybody knows it's 1, so you don't have to put that there. So when there's only one group on a ring, you use no number, one alkyl group. Therefore, 6 carbons, cyclohexane, and now we have isopropyl group, and they're done. Now, if we look at K, what do we have? Oh, we have a ring. How many carbons? 1, 2, 3, 4, 5. Pentane, it's a ring, cyclopentane. Now we have a terbutyl. I was going to say T-butyl, I promise. I wait till next week to start doing that. And an ethyl group. Now, the correct Iupac is the alkyl group with the highest alphabetical priority. That's the one closest to the front of the alphabet, gets the lowest number, 1. Well, you ignore the prefix tert, so this is a B, this is an E, that gets 1. And then you go clockwise or counterclockwise, and that's important, clockwise or counterclockwise from that group to number the rest of the alkyl groups. So this would be 1 tert-butyl, 2 ethyl. This is an ethyl group, tert-butyl, cyclopentane. However, I would accept 3 other answers. One would be, if you put the 2 ethyl first, the 1 tert-butyl second. The next one is if you change the 1 here to 2 and the ethyl being 1. And finally, if you do that and also switch the order. And let's have you try one. And the question would be, what is the Iupac name for the following molecule? 3 points each. Your turn to have some fun. And remember, when you're up, give me the thumbs up. Or if you want, you can use any other emoji you like. I don't think Zoom lets you use your own. That would be wild. I get in a lot of trouble then. All right, I think everybody's done. Now, the first thing you notice is, oh, look, I have a ring. How many carbons in the ring? 1, 2, 3, 4, 5, 6. That was an alkane, hexane. But it's a ring. Hold on 1 second. I better give myself more room here. And this happens even in face-to-face on a board if I'm getting too close to the end of the board. 6 carbons is hexane, but it's a ring, so it's cyclohexane. And now 1 carbon here is a methyl group, 3 carbons, and notice this to the N carbon to the ring is N-propyl. So this would be methyl, N-propyl, but I'm not done. I need a number. And here, this would be 1, this would be 2, 1-methyl, 2N-propyl cyclohexane. Now, if you have the numbers switched, that's okay. If you have the orders switched, that's okay. If you have the numbers and orders switched, I'll allow that on test. And that's how you do that. Now, there are two skills actually you need in organic chemistry. And that's one skill when it comes to nomenclature is here's the structure, what's the Iupac name? The other skill is here's the name, draw the structure. So how do you do that? Well, you look and say, oh, methane, and you learn that table, 1 carbon. And one of the things you should always remember, how many bonds to carbon? 4. Oops, let me fix that finger. 4 bonds to carbon. Yes, 4, 4, 4, 4 bonds to carbon. 1, 2, 3, 4, 4 bonds to carbon. And that's how you know how many hydrogens should be on a carbon when you draw the structure. And if we look at butane, here we have 4 carbons, butane, and it's a straight chain. Notice the first one, this carbon has 1 bond to this carbon, so 4 minus 1, 3 hydrogens. And this carbon has a bond to this carbon, bond to this carbon, 2 bonds, 4 minus 2, that's why there are 2 hydrogens. Now, if we look at C, how do you decode this? Because now it's getting a little more complex. You start from the right and move left. One of the things I can't draw on a PDF file, unfortunately, start from the right and move left. Pentane, the root name, 5 carbons. On carbon number 2, it's your old friend, the methyl group. So I have 5 carbons, carbon 2, CH3, and notice I have the right amount of hydrogens. We look at this carbon right here with a 1 hydrogen. Why 1 hydrogen? 1, 2, 3 bonds to carbons, 4 minus 3, because carbon always has 4 bonds, and that's why there's 1 hydrogen. Now you could have put the methyl group over here and started counting 1, 2, and that would have been correct. Now, if we come over here, we have 2, 3, and I forgot the dash, it fell off. Bad, Dr. White. Dimethyl hexane. How do you decode it? Start from the right, move left. Hexane, 6 carbons. Methyl, CH3. Di means 2, tri means 3. Di means 2 methyl groups. Where are they on carbons 2 and 3? It's carbon 1, therefore this is 2 and 3. And that's how you do it. Now, if we look at G, we have cyclobutane. Again, start from the right. Butane, 4 carbons, cyclo, it's in a ring. You call this a square, organic chemists like me call it a ring. And I made a mistake that I haven't corrected it yet. I should, the way I have the name written. That should be 1 tert-butyl first, 2 ethyl second. And even the way I have it written wrong, we start here, pentane, 5 carbons, cyclopentane, 5 carbon ring. And then on 1 carbon is T-butyl or tert-butyl, which is this. And then on the other carbon right next to it is ethyl. And I'm going to let you have 1 too, and maybe even 2. why don't you try this one first? Draw the structure for 4-isopropyl decane. Have some fun. And remember, when you're done, give me a thumbs up. Or any other emoji you'd like to use. All right, I think everybody's done. I'll give you another couple seconds. All right, how do you decode this to know what to draw? Well, you start from the right and move left. And the first thing we see is decane. And hopefully you've learned that table of the alkanes 1 through 10. 10 is decane. So I better get to work. And now I have 10 carbons, and I see isopropyl. That's 3 carbons. The center carbon of the alkyl group is bound to the chain. Where is it on carbon 4? 1, 2, 3, 4. Remember, always start numbering from the end of a chain. And I have my isopropyl. And now I'll go in and put in my hydrogens. And that's how you do it. Oh, let's do another one. These are fun. And why don't you draw the structure of 1-N-butyl 3-ethyl cyclohexane? I see one person done. Anybody need more time? All right, I'm going to go ahead. Well, I'll give you another 8.7 seconds. 7.2, 7.4, 7.6. I have a slow clock today. 8. All right. How do you decode this to know what to draw? Well, you start from the right and move left. hexane, 6, but cyclohexane, that's a ring with 6 carbons. And then I have an ethyl group on carbon 3 and an butyl group on 1. If I call this carbon 1, and butyl is 4 carbons, the N carbon is bonded to the ring or chain. And then you can go clockwise or counterclockwise. Most of you are going to go clockwise, so I will. And we have an ethyl group, and an ethyl group is 2 carbons, and that's fine. By the way, if you have this right here going this direction where you had carbons on this side, the 4 carbons bond to ring, that's okay, because there's free rotation around the carbon-carbon single bond. Now, let's look at J, and here we have 2,3,5 trimethyl octane. We go from the right, octane, 8 carbons. 1, 2, 3, 4, 5, 6, 7. Oh, I got it right. And next, methyl, you know, is CH3. Remember, di is 2, tri is 3, and that's 2, 3, and 5. This is 1. That's 2, 3, 4, 5. And that's how you do it. Now, on my test, I'll have 3 types of areas of questions. The first one is, I call it general knowledge. Example, let's see, what can I ask on a test general knowledge? Oh, I've got a good one. Let's see if you know this one. How many bonds to carbon? And you're right, 4 bonds to carbon. That's general knowledge. Now, the other type of questions I put on a test are nomenclature. That is 2 types of nomenclature questions. One is, here's the structure, give the Iupac name, the official name. The other one is, like we just did, here's the name, draw the structure. And finally, a third area I put on test, and this is the same through 1, 2, 3, 4 in the final. It either is general knowledge, nomenclature, and the last one is reactions. And reactions, most of the time, I will be asking you give the product or products. Today, I'll teach you another one later on. Not wrong place. And hopefully you all see the problem set on your screen. If not, always feel free to yell, I don't see it. Thank you, Joanna. All right, now, give the reaction product or products to the follower. Remember, at the base of the arrow, you have your reactants or starting materials. At the head of the arrow, the products, what you make. And how do you do this? You look and say, what's that? That's propane plus oxygen. And I don't have it on here, but let me go to my whiteboard. How do you do a reaction like this? You look here and say, what's different about that? Oh, that's an alkane. Here we have plus oxygen, and this could have also been a cycloalkane. And this is the general reaction that you have to memorize. The products are carbon dioxide plus water. Now, in a reaction, it doesn't matter which goes first or second. You could have put water plus CO2. It's the same thing. If I have a penny and nickel in my hand, and I say, oh, look, I have a penny nickel in my hand, or I say I have a nickel and penny in my hand, it's the same thing. same thing in order of writing down the products. So if I have an alkane, which propane is, reacted with oxygen, I'll get CO2 plus water. And I'm done. And if we go back and look at the problem set, that's the answer. And B, that's an alkane plus oxygen. That too gives CO2 and water. Remember, in my class, you do not balance chemical equations. Excuse me. And finally, the last one, we have a ring, cyclohexane plus oxygen, the same general reaction. Cyclohexane or alkane, oxygen gives CO2 and water. And that's the first problem set. Any questions on alkanes, or cycloalkanes, nomenclature, or reactions? Well, in that case, oh, I better ask something. I almost forgot. Did any of you happen to pass by a gas station and think about the gasoline contains, half the weight of gasoline contains alkanes? Did you? Did you happen to look at a candle? I have a collection of candles because I worked for this Anglo-Dutch company, which originally started as a Dutch company. They made chemicals which they used to make candles. And that was located in, oh, here's the interesting thing, Gouda. How many of you have heard of Gouda cheese? Anybody? Well, Gouda cheese is a really good cheese, and it's spelled Gouda. And that's because it comes from the city originally in the Netherlands called Gouda. But Gouda is how Americans pronounce it. It's not how the Dutch pronounce it. Because I know Hebrew, I can speak Dutch words most Americans can't or have trouble. And Gouda, if you're in the Netherlands, is pronounced Gouda. And I worked in Gouda at times, and it was beautiful. I'd take the train from, how many of you have heard of the big city where the international court is in the Netherlands called The Hague? That's the American way. The Dutch way for that name is Den Haag. And I stayed in a hotel in Den Haag, took about a half-hour train trip to Gouda. I walked from the train station to the chemical plant research center I worked at for the company I worked at when I stayed there. And it was beautiful because I walked right through the town center of Gouda. And there they had the town hall and surprise, surprise, the cheese warehouse that was already quite old before Columbus set sail. Think about that. It was just a beautiful way. And I also walked down some canals to get to there. It was about a beautiful 10-minute walk, except when it was raining. Even then, it wasn't too bad. All right, but half the weight of a candle is that, alkanes. And did you happen to think about if you use natural gas or your barbecue propane, those are alkanes. You should. That's the fun about organic chemistry, thinking about where we use it and knowing about where we use it. And you'll learn more about that this semester. All right, any questions before I move on? All right, yesterday we started talking about reactions. And I talked about hydrogenation. That's where anytime you take a double bond and you react with hydrogen, the catalyst can be platinum, palladium, or nickel. You break the pi bond. Remember, double bond is a pi bond and a sigma bond, and each carbon gets a hydrogen. And another way of showing that, showing just a double bond, hydrogen, and a catalyst, and I'll abbreviate. And the catalyst can be nickel, platinum, or palladium. And you break the pi bond. Remember, this has one pi bond, you should know, and one sigma bond. And each carbon gets a hydrogen. Oops, Dr. White made a mistake. He's corrected it. And why don't you try this one? What would be the product or products, organic product or products, for the following reaction? 3 points each. When you're done, give me a thumbs up. It'd be fun if they had a thumbs down, but they don't. All right, I think everybody's done. So I'm going to get to work. And when you look at an organic molecule, you should look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen atom. And right here, ooh, a double bond. And immediately, this is all I see, because that's where the fun is, and that's the only place the action is going to happen. And we're reacting this with hydrogen and a catalyst, where the catalyst can be platinum, which it is, palladium, or nickel. And you break the pi bond, each atom of the double bond gets a hydrogen. Now, do you break carbon-carbon single bonds? No, you don't. And therefore, I have 1, 2, 3, 4, 5 across. On this carbon, I have a methyl. On this carbon, here are my 2 carbons of double bond. I break the pi bond. Each one gets a hydrogen. I know there are 4 bonds to carbon, so I can put in the rest of the hydrogens. And that's how you do it. Oh, let's try another one of these. And why don't you try this one? What would be the product or products for the following? You're doing organic chemistry, and hopefully it's not too painful. Might even be fun. It is. Yeah, I think everybody's done. So I better get to work. Well, you look at an organic molecule. Oh, I got a ring. That's mainly carbon-carbon single bonds, but wait, I have a double bond. I'm reacting it with hydrogen, and nickel is a catalyst. Remember, the catalyst can be nickel, platinum, or palladium. And the double bond has one pi bond, one single or sigma bond. You break pi bonds, but not sigma bonds. And each carbon of the double bond has a hydrogen. Now, do you break carbon-carbon single bonds? No. So I started with a ring with 5 carbons. I better end with a ring. It also had a methyl group here and an ethyl group here. Now, notice these 2 carbons are my double bond, which are these 2 carbons. And this has, each one has 1 hydrogen. On a ring, you don't show hydrogens, so I'm done. And if we count, this one has 2 hydrogens now, this one, so it's gone from 1 to 2, and I did add my hydrogens, and that's how you do that. Now, the other reaction we talked about yesterday, notice I say we, I talked about you listen, and that was when you take a double bond, halogenation, and react it with halogen gas. Remember, X is abbreviation for halogens, and here we have a double bond reacting with halogen gas. This one's energetic, so you don't need a catalyst. And as I have above, but I'll write again, X is fluorine, chlorine, bromine, or iodine. And remember, we have 1 pi bond, 1 sigma bond. You break the pi bond. In this case, each carbon of the double bond gets a halogen. And here's one for you to try out. What would be the organic product or products for the following reaction? And remember, when you're done, give me an emoji. That's not right. Click on the emoji in Zoom. Look in the mailbox and somebody's mailed me an emoji. No, no, no. All right, let's do it. What's different in this molecule? A double bond. What am I reacting with? Chlorine gas, Cl2. We use that for halogens. And you break the pi bond, each carbon gets a halogen. I have 4 carbons, better end up with 4 carbons. These 2 carbons are the double bond, break the pi bond, each one gets a chlorine. Chlorine bond counts as 1 bond to carbon, so this would have 1 hydrogen. This has 2 bonds, 4 minus 2, 2 hydrogens, and I'm done. Now, if I look at the clock, went a whole minute over, so let's take a break. I'll see you in 5 minutes. Come back at 1:56 by my clock, or 5 minutes from now by your clock. I can go stretch. Everybody back? Let's get going. Let's do one more example of halogenation. And why don't you try this one more example? And when I say try it, the question is give the organic product or products for the following. And for you at home watching on YouTube, hi. But that was awful. All right, I think everybody's done. And what you do, you look at the molecule, look for what's different. What's not a carbon-carbon single bond, carbon hydrogen. And you look right here and say, oh, a double bond. What am I reacting it with? Iodine gas or iodine, diatomic iodine. And that's halogen. Remember, X can be fluorine, chlorine, bromine, or in this case, it's iodine. And you break the pi bond. Remember, double bond has one pi bond, one sigma. And guess what happens? Each carbon of double bond gets a halogen. Well, do you break carbon-carbon single bonds? No. So I have my ring, and over here I have a methyl group. And over here I have my ethyl group. Now, these are my two carbons of double bond, these two, which will get the halogen, which are these two carbons. Halogen, in this case, is iodine. And that's how you do it. Now, if you look at the reactions we just went over, either adding hydrogen or halogen to a double bond, each carbon of the double bond gets the same thing, either a hydrogen or a halogen. And we call that symmetrical addition. Now, what happens if they're not the same? If you're reacting something where one carbon gets one thing and the other gets another thing. And this was a very challenging problem to solve. And a great Russian chemist, organic chemist, Markovnikov, solved this and determined and developed what's called Markovnikov's rule. I'll never ask on a test what's Markovnikov's rule, but I will expect you to know how to use it. Let's look at it. Now, if you look on the slide, and do not write this down or memorize it, when an unsymmetrical molecule of the form HA or HQ adds to an unsymmetrical alkene, meaning double bond, hydrogen from HA or HQ becomes bonded to the unsaturated carbon atom that already has the most hydrogens. What does that mean? Well, let's take a look at one example we'll learn. Now here I have one example. I have it like this. Really a better way to write it would be like this. If you have a double bond and you react HX, where X again, in this case, is chlorine, bromine, or iodine. Why not fluorine? HF, hydrofluoric acid, is quite dangerous, quite expensive, and for this reaction, you wouldn't want to. I'll tell a story in a little while about HF. And what happens is you break the pi bond, and one carbon gets H, the other gets the X, and how do you know? You know because it follows Markovnikov's rule. And Markovnikov's rule is the carbon of the double bond with the most hydrogens gets the hydrogen, from HX, and the other carbon double bond gets the halogen. Let's see how that works. And sometimes I'll write the HX, just like with halogen gas, on top. Let's use HCl. Now, question is, what's the organic product or product of the following 3 points each? How do you do that? You look for what's different. Oh, a double bond. What am I reacting it with? HX, where X will be chlorine, bromine, or iodine. And you break the pi bond. One carbon gets H, the other gets X, and this follows Markovnikov's rule. When I first started teaching this, I used to write his name on the board, and I used to misspell it at times. Dr. White was always the first one down in the spelling bee, so I just abbreviate now M's rule. And M's rule, Markovnikov's rule, is the carbon of the double bond with the most hydrogens gets the hydrogen, the other carbon double bond gets the halogen. So if we look up here, I'm going to go Technicolor on you. This carbon has 2 hydrogens. This carbon has 1 hydrogen. And now you got to use your high-level math skills, which is the larger number. And hopefully all pick 2. So what does that mean? First of all, do you break carbon-carbon single bonds? No. So I'm going to have 3 carbons. Here are my 2 carbons double bond. This carbon has the most hydrogens and gets the hydrogen, and the other carbon gets the halogen, in this case chlorine. And the rest you fill in the hydrogens. And that's Markovnikov's rule. The carbon of the double bond with the most hydrogens gets the hydrogen from HX, and the other carbon gets the X. Now, when I learned it as an undergrad, my instructor had the following, which helped us remember it. And he said, the way to remember Markovnikov's rule is the rich get richer, the poor get poorer. And I'm talking about hydrogen. And that means the carbon with the most hydrogens gets the hydrogen, the rich get richer, and the other carbon and the poor get poorer. Another way he also said that, and why do I still remember this? Them that has it gets it. Them that has it gets it. So the one that has the most hydrogens, them that has it gets the hydrogen from the HX, and the other carbon gets the halogen. And I'll do one more, and then I'm going to let you have some fun too. Now, if we look at this reaction, question is, what's the organic product or products for the following? And we look here and we say, oh, look, a double bond. When we're reacting with HBr, I know bromine is a halogen, HX. Remember, X is the halogens, chlorine, bromine, or iodine. And you break the pi bond. One carbon gets H, the other gets X. That's better looking X. And it follows Markovnikov's rule. The carbon of double bond with the most hydrogen gets the hydrogen from X, and the other carbon double bond gets the halogen. And if we look here, here are my 2 carbons. How many hydrogens does this one have? 2. How many does this one have? 0. Which is the greater number? Time's up. Hopefully you pick 2. So the hydrogen will go to this carbon. Now, do you break carbon-carbon single bonds? No. So I have 3 across plus my methyl. Here are my 2 carbons double bond. Hydrogen goes here because this has the most hydrogens, and the other carbon gets the halogen in this case, bromine. And now I'll put in my hydrogens because I know there are four, just four bonds to carbon. Now, since I don't want to hog all the fun, I'm going to let you have some fun too. And there you go. Give the organic product or products for the following reaction. 3.6. Remember Markovnikov's rule, the rich get richer, the poor get poorer. For them that has it gets it, or the carbon of double bond with the most hydrogen gets the hydrogen from HX, and the other carbon gets the halogen X. And when you're done, I know one of you already have, give me an emoji symbol. All right, let's move ahead. Look at the molecule, what's different? Double bond. And now we say, all right, do we break carbon? We got, well, first of all, I'm getting ahead of myself. Double bond reacting with hydrogen chloride, HX. Remember, X can be chlorine, bromine, or iodine. In this case, it's chlorine. You break the pi bond, one carbon gets hydrogen, and one carbon gets chlorine. And if you want to turn off your microphone, if you have a question, feel free anytime to do that. And not chlorine, I'm getting ahead of myself. It should be X. And it follows Markovnikov's rule. Do you break carbon-carbon single bonds? No. So we have four carbons across and a carbon here, methyl. Here are my two carbons of the double bond. This has two hydrogens, this has one, which is the larger number. Hopefully all picked two. Therefore, my hydrogen goes there to this carbon, and this carbon gets my halogen, which in this case is chlorine. I know there are four bonds to carbon, so and there you go. Let me ask you, does everybody see that clearly on your screen? I don't want to go too, okay. Now, let's do one more. And before we do that, I have to tell you something, honestly, be honest with you. And that is Dr. White, Mother Nature, love rings, students don't. Why not? Well, here's why. If we have the following reaction, which I will do, what is the product, organic product or products, 3.C? What's different? What's not carbon-carbon single bond or a carbon or hydrogen atom? And here we have a double bond. And now we're going to add HI, which is really hydrogen halogen gas, or HX. And remember, X can be chlorine, bromine, or in our case, iodine. And you break the pi bond. One carbon gets H, the other gets the X. How do you know? It follows Markovnikov's rule. And I honor his great work by remembering and saying his name, which organic chemists do. And we look here and say, all right, I know I don't break carbon-carbon single bonds. So this is here. I break the pi bond, but Markovnikov's rule is the carbon with the most hydrogens gets the hydrogen, the other carbon gets the halogen, but I don't see any hydrogens here. Oh no, what do? Well, you count, and you remember there are 4 bonds to carbon. And if we look at this carbon, it has 3 bonds, 4 minus 3 is 1 hydrogen. And if we look at this carbon, it has 4 bonds, 4 minus 4 is 0. And now we can go ahead and say, which is the greater number, 1 or 0? And hopefully all pick 1. So that means the hydrogen goes to this carbon right here, and the other carbon gets the halogen, in this case, iodine. And notice, I don't show hydrogens on a ring, but it does have, instead of 1, it now has 2 hydrogens. And that's why students don't like the rings, because it's extra work. And it's your turn. Give the organic product or product for the following reaction. It looks like everybody's done. And now look here and say, oh, what's different? I see a double bond. Remember, what's not a carbon-carbon single bond, a carbohydrate. I'm reacting with HCl, which is HX. X can be chlorine, bromine, or iodine. I break the pi bond, and 1 carbon gets H, the other gets X from my HX, and it follows Markovnikov's rule. And do you break carbon-carbon single bonds? No. Excuse me. Getting all choked up over this. And therefore, this will be there. Here are my 2 carbons of double bond. Now we have to count hydrogens, or actually bonds first. This has 1, 2, 3, 4. 4 minus 4 is 0 hydrogens. This has 1, 2, 3. 4 minus 3, 1 hydrogen. Markovnikov's rule says the hydrogen goes to the carbon with the most hydrogen. Some that has it gets it, or the rich get richer and the poor get poorer, and the halogen goes to the other one. And therefore, the halogen will go to this carbon, and it's chlorine. Now, I have written that way for this class. You could have also written it this way. And both are correct. And that's how you do it. And that's how you add HX to a double bond hydrohalogen acid. That's what HX is. And follow Markovnikov's rule. Oh, wrong thing. Now, this is called addition of an acid to an alkene. Remember, alkene is double bond, acid HX. Now, let's talk about addition of water to an alkene, a double bond, sometimes called hydration of an alkene. And now I have to teach you a couple of things to understand the reaction. Double bond, that's what I'm showing here. Now here we have H plus. And what is H plus? H plus means acid catalyst. And examples would be stuff like sulfuric acid, other acids, which I'm not going to draw, but toluene sulfonic acid and methane sulfonic acid. And an acid, we remember from general chemistry, donates a proton, H plus. And you need that to make this go quicker. Now, water, you all know is H2O. Well, let's look at it and write it this way, HOH. And what happens is, remember, you have a pi bond and sigma bond, double bond. You break the pi bond, and from water, HOH, one carbon gets the H, the other gets the OH. By the way, OH is called hydroxy group or hydroxyl group. And this follows Markovnikov's rule. The carbon with the most hydrogens gets the H from water, and the other carbon gets the hydroxyl group, OH. And that's how you do it. And when you put an OH, hydroxyl group on a carbon, I'll teach you later in the semester, that's how you make what we call an alcohol. So let's do an example. And the question is, give the organic product or products for the following reaction. 3 points each. And we look here, what's different? A double bond. So I have a double bond. I'm reacting with acid plus water. Remember, water is H, OH, and you break the pi bond. One carbon gets H, the other gets the hydroxyl group, OH, and it follows Markovnikov's rule. The carbon in a double bond with the most hydrogens gets the hydrogen from water, and the other carbon gets the hydroxyl group. So do you break carbon-carbon single bonds? No. But I will break that pi bond. Remember, double bond is one pi bond, one sigma bond. And now I have to look at the double bond carbons. And this one has 2, this one has 1, which is the greater number, 2. So this carbon, the N carbon, gets the hydrogen, and the other carbon gets the hydroxyl group. Hydroxyl group counts as 1 bond to carbon, so I know how to put in my hydrogens. And that's how you do it. And why don't you try this one on your own? What would be the organic product or products for the following reaction? Let's see, one person is gone. Even though it's not erased, I try and give everybody time to finish. Yeah, I think everybody's finished. So let me go ahead and do the work. And if you look at the molecule, you look for what's different, what's not a carbon-carbon single bond or carbon or hydrogen atoms, and we see a double bond. Hopefully you won't have any nightmares hearing me say, look for what's different. And I have a double bond reacting with H+, which is acid catalyst, and water. And remember, water is HOH. And I'm going to break the pi bond. Remember, this has one pi bond and one sigma bond. And one carbon gets H, the other gets the hydroxyl group OH, and it follows Markovnikov's rule. Markovnikov's rule is the carbon double bond with the most hydrogens gets the H, the other gets the OH. And we come here, we have our two carbons double bond. This has 1, this has 0. Which is the greater number? And time's up. Hopefully all picked 1. Therefore, you break carbon-carbon single bonds, and the answer is no. So I have 4 carbons across, and my methyl group. Here are my 2 carbons of the original double bond. To this carbon goes the hydrogen, and this carbon gets the hydroxyl group OH, and I'll put in my hydrogens. And that's how you do, oh, let's do one more. Of course we will. Your turn. Give the organic product or products that are following. Hopefully you're having fun doing these. All right, I think everybody's finished. So we look at this molecule, we look for what's different. Oh, a double bond. I'm reacting it with acid, H+, and water. And don't forget, water is HOH. You break the pi bond. One carbon gets the H from the water, the other gets the hydroxyl group OH. How do we know which is which? It follows Markovnikov's rule, and that is the carbon double bond with the most hydrogen gets the hydrogen, the other one gets the hydroxyl group. And oh no, there are no hydrogen. Yes, there are. You just don't show them on a ring. If we look at this carbon right here, it's got 1, 2, 3 bonds. Remember, there are 4 bonds to carbon, so it has 1 hydrogen. We look at this carbon right here, it has 1, 2, 3, 4. It has 0 hydrogen. You break carbon-carbon single bonds? No. So here's my ring. My methyl group is there. My ethyl group is here. And this carbon gets a hydrogen, which I'm not going to show. This carbon gets the hydroxyl group. And that's how you do it. Now, one of the things I would like to remind you is, why am I learning these general reactions? Because these are the reactions that we use to make things. Make things like this bottle, the dye for my shirt, the Mother Nature to make some of the molecules in my shirt, and other things. And we'll learn certain general reactions later in the semester that you're stomach uses, yeah, there's organic chemical reactions going on in your stomach to break down your food. So that's why we're learning these general reactions. All right, next thing I'd like to talk about are the alkynes. Now, the alkynes, just to remind you, are acyclic unsaturated hydrocarbons, which one or more carbon has one or more carbon-carbon triple bond. Remember, triple bond is designated by 3 lines between 2 carbon atoms. Now, the triple bond is linear, unlike a double bond, which I don't show when we're doing reactions, but for nomenclature, I do for double bond, so you can see if it's cis or trans, but that doesn't exist in there. And the important thing is they undergo the same reactions as alkenes that I'll teach you this semester. There's some that are different, but I won't get into that, except you have not one, but 2 pi bonds. Now, remember this as 2 pi bonds and 1 sigma bond. So we have 2 pi bonds and 1 sigma bond. And the nomenclature, which we've already done, is similar to alkenes. Instead of using the E on the ending, we use a Y on the ending. And there's no cis-trans isomerism. So let's look at the first reaction. Remember, R means anything with carbons and hydrogens. I should have put R prime there. But another way of this is take a triple bond and react it with hydrogen. And something you're going to see here, bracket, close bracket, excess, and then a catalyst. And just like with a double bond, the catalysts are platinum, palladium, or nickel. And unlike a double bond, we have 2 pi bonds here, but 1 sigma, or single bond. You don't break that, but you break 2 pi bonds. Each time I break a pi bond, each carbon will get a hydrogen. But since there are 2 pi bonds, each carbon will get 2 hydrogens, which means you use 2 moles or molecules of hydrogen. Organic chemists are lazy. We don't want to have to balance the equation, so we use this. Bracket the letter X and then the letter S, close bracket, means you have all the hydrogen in the world to react with anything hydrogen will react with. That is abbreviation for excess. Isn't that cute? The letters X and S, excess. And that means you don't have to balance it. You have all the hydrogen in the world with anything that will react with hydrogen. So let's take a look at this reaction. And the question would be, give the organic product or product for a following reaction. And now I look and say, what's different? What's not a carbon-carbon single bond or carbon-hydrogen atom? Oh, a triple bond. I'm reacting with hydrogen, excuse me, and I have excess hydrogen. That means I have all the hydrogen in the world, anything hydrogen can react with. And I have palladium, which is a catalyst. Remember, you have palladium, it can be platinum or nickel. And what happens is, remember, a triple bond now has 2 pi bonds and a sigma bond. So you don't break the sigma bond, but for each pi bond, each carbon of the triple bond gets 2 hydrogens, and therefore, actually more than 2, each pi bond gets 2, 2 pi bonds, each carbon gets 4. You break carbon-carbon single bonds? No. And my 2 carbons of the triple bond each get 2 hydrogens. And that's how you do it. And why don't you try the following? What would be the organic product or products for the following? It looks like everybody's done, so I better get to work. If we look here, what's different? What's not a carbon-carbon single bond, carbohydrate? A triple bond. What am I reacting with? Hydrogen, but it has this letters in bracket X and S, which mean you have all the hydrogen in the world that will react with anything hydrogen could react with, and we have a catalyst. And the catalyst can be, in this case, platinum, could be palladium, or nickel. And you break the 2 pi bonds, not the sigma bond, and each carbon of the triple bond gets not 1, but 2 hydrogens. You break carbon-carbon single bonds? No. So I have 1, 2, 3, 4 cross plus this methyl. I break the 2 pi bonds, and each one of these carbons of the triple bond gets a hydrogen. And here, and you could have written this CH2 and this CH3, but I try and make things easy for you on my tests, so you don't have to. And that's how you do that. Oh, let's do one more. And there you go. What would be the product or products for the following reaction? All right, looks like everybody's done. If we look here, what's different? Ooh, a triple bond. What am I reacting it with? Excess hydrogen and nickel, which is a catalyst. And the catalyst can be nickel, platinum, or palladium. I have some stuff at the bottom of my screen. I don't think you can see, but I can. So that's why I put that over there. And don't forget, a triple bond has 2 pi bonds. That's something you should know. And sigma bond. And therefore, you break the 2 pi bonds, and each carbon of the double bond, triple bond, not double bond, triple bond, gets 2 hydrogens. You break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5, 6 across. On this carbon, I have 2 carbons, methyl groups, and here I have a methyl group. And here are my 2 carbons of my triple bond, and each one gets 2 hydrogens. And now I can put in the rest of the hydrogens, so I know there's 4 bonds to carbon. I should put that carbon down there, sorry. And that's how you do it. And that's hydrogenation of an alkane. Alkyne, I'm sorry. All right, let's take a look. My computer is being funky again. Let me try something. Nope, that didn't work. You know something? Let's take a little longer break. Come back at 2:45, and I'll see you in about 5.5, 6, 7 minutes. We're doing good today, so I'm gonna give you an extra minute or so break so I can fix this. Are you all ready for home stretch? All right, let's get back to alkynes triple bonds. I just talked about hydrogenation of an alkyne. Now, the other reaction for alkynes is a triple bond reacting with halogen gas. And once again, we use triple bond. And because it has two pi bonds, we need more than one molecule or mole of halogen gas. And therefore, again, we use the symbols bracket, letters XS, close bracket, meaning you have all the halogen gas excess to react with anything it would react with. In this case, for each pi bond, each carbon of the triple bond gets a halogen. For two pi bonds, you get two halogens. And that's how you halogenate a triple bond. All right, and let's take a look at this. Let me do one thing. One thing I haven't mentioned, but I assume that I shouldn't, it's important which carbons you put the halogens or whatever you're adding on. Otherwise, that's not what you get in real life, meaning that's the wrong answer on the test. All right, let's look at the following reaction. I haven't used this in a while. And the question is, what would be the product or products of the following reaction? Organic product or products. We look for what's different, a triple bond. And we're reacting with fluorine gas, F2, which is a halogen. For this reaction, F can be fluorine, chlorine, bromine, or iodine. And for each pi bond, remember this has two pi bonds, one sigma bond. Each carbon of the triple bond gets a halogen. Since we have two pi bonds, each one gets two halogens. So you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5. Because I started with 1, 2, 3, 4, 5 carbons. Here are my two carbons of the triple bond. I broke both pi bonds. As you see, there's only one line between them right there. And now each one gets not one, but two fluorines. And I can put in the hydrogens. And now I'm going to let you have some fun. And the question would be, give the organic product or products for the following. 3 points each. All right, looks like everybody's done. We look at this molecule, what's different? Well, it's not a carbon-carbon single bond or carbon hydrogen, a triple bond. And now, what are we reacting with? Br2, and that's halogen gas. And notice we have excess, and X can be fluorine, chlorine, bromine, or iodine. In this case, it is bromine. And don't forget, 2 pi bonds in the triple bond and a sigma bond, which we don't break. I've broken it. Each carbon of the triple bond gets 2 halogens. And notice we have 4 across and a methyl group. Do you break carbon-carbon single bonds? No. So we have 4 across and a methyl. Which are my 2 carbons of the triple bond? These 2, which are these 2, and each one gets not 1, but 2 bromine. And that's how you do it. Oh, let's do one more. And why don't you try this one? What would be the product or products of the following reaction? 3 points each. All right, looks like everybody's done. If we look here, oh, I've got a ring, but that's only carbon-carbon single bonds. What you look for what's different, what's not carbon-carbon single bonds or carbon-hydrogen atom, a triple bond. That's different. Now, do you break carbon-carbon single bonds? No. And what I did here in this example was the chemistry instructor's favorite trick on a test. I gave you a big, scary molecule. No, it's not scary. You just know this is a triple bond reacting with halogen gas, chlorine, and it's excess. And X, just to remind you, can be fluorine, chlorine, which it is in this case, bromine, or iodine. And you break the 2 pi bonds, and each carbon of the triple bond gets 2 halogens. So I'm not going to break carbon-carbon single bonds. I have my ring, this carbon with this carbon, and these 3 carbons. Here are my 2 carbons of my triple bond. Notice I broke the 2 pi bonds, and each one gets not 1, but 2 halogens, in this case, chlorine. And that's how you do it. All right. Next couple things I don't have slides for, so pay attention. You can always go back to the video to watch. Now, the first thing I'd like to talk about is the following. Now that I've taught you about excess the letters X and S in a bracket, meaning you have all the reagent or chemical you need to react whatever it will react with. Let's look at the following. If you notice the molecule, first of all, everybody see the molecule on the screen I just draw? Thumbs up, people. Thank you, Joanna. All right, now notice what's different. Oh no, it's got a double bond. Wait, it's got two double bonds. Now, when you have double bonds in a molecule, there are two types of situation. This is one of them. I'll call A for now, and the other one is B. Now, this I'll never ask on a test, but I will use the terminology. When you have two double bonds and they're not separated by any carbons, the carbons in the double bond are connected together. This is called conjugated. Double bonds. I'll never ask this on a test. Now, when they're separated by one or more carbons, it's no longer, it's non-conjugated. I can spell it. Now, the chemistry of B conjugated double bonds can get very complex, and I will not be teaching that in this course. Yes, I do know how to do that, but I will not teach that in this course. There are other things I'd rather spend more time on later on, like carbohydrates, proteins, and fats and oils, because most of you are in health-related majors. Now, when it's non-conjugated, I will teach that. And when it's non-conjugated, each double bond reacts like it's alone. When it's non-conjugated, each double bond reacts like it's alone. So let's look at the following reaction. And the question is, give the organic product or product for the following reaction. We look up here, what's different? Ooh, a double bond, another double bond, and it's non-conjugated, so each one reacts like itself. So I have hydrogen and a catalyst, and the catalyst can be nickel, platinum, or palladium. And now what happens? You break the pi bond, and each carbon of the double bond gets a hydrogen. But wait, Dr. White, why do you have the excess? Because you have two double bonds. You need twice as much hydrogen, but organic chemists are lazy. We are, but we don't want to balance a chemical equation. So that's why the excess is there. That tells you have all the hydrogen in the world that will react with anything hydrogen will react with, which in this case is a double bond. You break carbon-carbon single bonds? No. So I have 5 carbons. Here are my 2 carbons of the first double bond. I break the pi bond, and each one gets a hydrogen. And then the second double bond, I break the pi bond, each one gets a hydrogen. I know there are 4 bonds to carbon. And that's how you do it. And why don't you try this one? What would be the organic product or products of the following reaction? 3 points each. And if you finish early, please be patient. I give time for everybody to finish up. And don't forget, give me a thumbs up when you're done. All right, let's do it. If we look at the molecule, what's different? Oh, a double bond here. Wait, a second one. And they're not conjugated, non-conjugated. And what do I have? Well, essentially, each one reacts like it's alone. Double bond. What am I reacting with? H2, hydrogen, and a catalyst. And the catalyst can be platinum, which in this case it is, palladium, or nickel. And you break the pi bond. Remember, double bond has 1 pi bond, and each carbon of the double bond gets a hydrogen, and you break that pi bond. I have 1, 2, 3, 4, 5, 6 cross plus the methyl. 1, 2, 3, 4, 5, 6 plus the methyl. This double bond, I've broken the pi bond. Each one gets a hydrogen. This double bond, I do the same thing. And now I know there's 4 bonds to carbon. And that's the product you get. Oh, let's do another. These are fun. And I'll let you try this one on your own. Let's see if you can work it out. All right, let's get going. We look here. Oh, we have a double bond. No, we have two of them, and they're not conjugated because they're separated by more than one carbon or more. And what do we have here? We have HX and we have XS. That just tells us I have all the hydrogen bromide that I need to react with anything that hydrogen bromide will react with. And here we have double bond HX. X can be chlorine, bromine, or iodine. In this case, it is bromine. I break the pi bond. One carbon gets H, the other gets X, and it follows Markovnikov rule. The carbon with the most hydrogen gets the hydrogen from HX, the other one gets the halogen. And why do I need HX here? Excess, HX, excess, bracket, letter X, letter S, close bracket, excess, because I have more than one double bond to react with. So you break carbon-carbon single bonds. No, I have 1, 2, 3, 4, 5, 6 across. And the first double bond are these two carbons. And notice this carbon has 2, this one has 1. Markovnikov rule says the H goes to the carbon with 1, and the halogen, in this case bromine, goes there. Now let's look at this double bond, and here are the two carbons. And here again, we have 2 and 1. This says more hydrogens. That carbon will get this hydrogen. This carbon will get the bromine. And that's the molecule you get. Oh, let's do one more. Remember when you have pi bonds, so far I've only done double bonds. Let's do a triple bond too. And why don't you try this one? What would be the product or products of the following reaction? 3 points each. And while you're doing that, I'll be right back in a minute. All right, I'm assuming everybody's done. Let's take a look at this one. This is an interesting molecule. And notice what's different. Oh, look, we have a triple bond, and then we have a double bond, and we're reacting with a halogen. So we actually have two general reactions. Double bond with halogen will do this. And triple bond, you break the 2 pi bonds, and instead of each carbon of the double bond gets like 2, each carbon of the triple bond gets 4, instead of 1, gets 2 halogens. In both cases, X can be fluorine, chlorine, which it is in our case, bromine or iodine. And the excess tells us I have all the chlorine that anything that chlorine can react with will. Now, do we break carbon-carbon single bonds? The answer is no. I have 1, 2, 3, 4, 5, 6 across. Now, these 2 carbons right here are a triple bond. So we'll use that general reaction, and each one gets 2 chlorines. And these 2 carbons right here are double bond, and we'll use this general reaction, and each one will get 1 chlorine. And now I'll put in my hydrogens. Could have put it on this side or that side. And that's how you do it. And now we're getting into some really exciting stuff. Now, another thing I don't have a slide for, because I don't need one, is no company is ever going to hire a PhD chemist, organic chemist, or even a bachelor degree chemist to do the following. Could you please tell us what happens when we mix this and this together? What do we make? No, they're not going to hire you for that. What they will hire you is, how do we make these molecules? Because we want to sell them, make a lot of money, and also help people. And that's called synthesis. Synthesis is a fancy word meaning to make. By the way, Dr. White's training, my PhD thesis was in synthesis of certain compounds, how to make certain compounds, because I joined a group, so I would be trained and get a PhD in synthetic organic chemistry, how to make things, which I have done throughout my career. So how do you do synthesis? Let's look at the following. And the question would be, what would be the starting material that you react with chlorine to make this molecule? Well, how do you do that? Well, you look at that and say, what's different? What's not a carbon-carbon single bond or carbon or hydrogen atoms? Oh, look, 2 chlorines, and they're on adjacent carbons. Adjacent means bonded to each other or next door to each other, whichever you'd like to use. And it looks like this. Remember, X can be fluorine, chlorine, bromine, or iodine. In this case, whatever we're starting with, we're reacting with halogen gas. And here's where you got to know your general reaction. What is that? A double bond. Now, once again, let's look at this reaction. Right here, whatever the question mark is, are we adding any carbons to it? And the answer is no. So if we end up with 3 carbons, I better start with 3 carbons. Again, I'm not adding any carbons, so if I end up with 3 carbons, I better start with 3 carbons because you can't make, they just don't magically appear. Be nice, but they don't. Now, if we look at the general reaction here, the 2 carbons with the halogen are the 2 carbons of the double bond. So therefore, if these 2 carbons have the halogen, then the double bond has to be there. And this is the molecule you start with. And if you notice, if I take this, react it with chlorine, I will get this product. And that's the fun part of synthesis. And the question is, what would you start with and react it with bromine to make that molecule? 3 points each. Your turn. Have fun. This is the exciting part of organic chemistry, synthesis. If you're done early, please be patient. I try and give everybody time to finish. Finish. All right, I think everybody's done. Let's do this. If we look at this, we say, what's different? What's not a carbon-carbon single bond, carbon or hydrogen? We look here, we say, oh, look, bromines on adjacent carbons. And bromines, we know, are halogens. And now we look at this and say, what do we react halogen gas with to make a dihalogen compound where they're adjacent next to each other? Remember, X can be chlorine, fluorine, bromine, or iodine, in this case, and that's a double bond. And notice the 2 carbons of the have the halogen are the 2 carbons of the double bond. Have we added any carbons? No. So we end up with 2, 4, 5 plus these 2, 7. We better start with the same thing. Which 2 carbons have the halogens? Right there. Therefore, they're those 2 carbons right there. Have a double bond. And now I can put in my hydrogens. And that's how you do it. Oh, let's do two more because Dr. White's having a good time. And let's take a look at this one. And now if we look at this, the question is, what would be the starting material? I'll do this one. And we look for what's different. Oh, we've got a hydroxyl group on a carbon. Hydroxyl being OH. And we're reacting with H plus and water. And I know water is HOH. And I remember adjacent carbon has a hydrogen. And what do we start with? A double bond. And this follows Markovnikov's rule. Now, if we come up here, or we'll first start here, the carbon with the hydroxyl group is one of the carbons of the double bond, and the adjacent carbon with the hydrogen is the other carbon. So now, if I look at this, I say, well, this carbon is adjacent, and this carbon is adjacent. Wait, it's got a hydrogen. Oh, we're in luck. So, do you break carbon-carbon single bonds? No. And we're not adding any hydrocarbons here. So I have these four plus these two. This carbon was this carbon. And this carbon here has to be in a double bond. But there's only 4 bonds to carbon, so I can't go to that carbon. So I have to go to this carbon. And now put in the hydrogens. And that looks ugly. Let me redraw it. And that's how you do it. Now, this is a little more tricky. Now, let me go through it again. What did I have? I looked for what's different, what's not carbon, what's not hydrogen, what's not carbon, carbon single bond, and that oxygen with a hydrogen gave it away. And I'm reacting it with acid and water. And how do you put a hydroxyl group on a carbon with acid and water? You start with a double bond. So I knew the carbon with the hydroxyl group had to be one of the carbons of the double bond, and an adjacent carbon, one next door, had to have a hydrogen in the molecule we ended up with, which is looking better this way. And if you follow Markovnikov's rule, the hydrogen will go here and the hydroxyl group will go there. This might be a little tricky, but let's see if you're up to it. What would be the starting material to react acid and water, H plus H2O, to make that molecule? Have fun. Like I said, this one's pretty hard. So if you're having trouble, don't be worried by it. All right, anybody need more time? Well, let's look at the molecule we're trying to look at, make, and what's different, what's not a carbon-carbon single bond or carbohydrate. Ooh, an oxygen with a hydrogen hydroxyl group. And adjacent carbon has a hydrogen. Why do I put that there? Because I know the general reaction when I stop hiccuping. Water and acid catalyst as hydroxyl group 2 and double bond. And this follows Markovnikov's rule. And if we look here, the carbon with the hydroxyl group has to be one of the carbons in a double bond. Now look at the two adjacent carbons, this one and this one. First of all, are we adding carbons? No. Uh-oh, I'm having a bad ring drawing day. Let's try that again. This carbon right here is this carbon. It has to be this carbon. Now, if we look at this carbon, it already has 4 bonds to it. So the only place I can draw a double bond is to this carbon, which is adjacent on this side, which I will. And that's the molecule you get. Now, let me show you something that's wrong. And how do we know it's wrong? If we look at this carbon, there's 1, 2, 3, 4, 5. 5 bonds. And the answer to that is no. And that's why that's wrong. So remember, your friend is there's always 4 bonds to carbon, never more. Now, if you notice, those synthesis problems are quite challenging. And because the Supreme Court of the United States, at least as of this moment, has outlawed cruel and unusual punishment to students, on test number 1, I will have only 1 synthesis problem for any of the general reactions we'll talk about, but only 1. Because when I put more, that would be cruel and unusual punishment. I can't do that. Now, test 2, you've learned more organic chemistry, so only put 3. When I was undergrad, because I was a chem major, the instructor I had put a lot more, and boy, those tests were challenging, but I'll only do 1. So now, if we go back to my slides for this chapter, we'll see. I get there. We've done this. We're done with the chapter. We finished this chapter on alkanes, alkenes, and alkynes. So you know what that means? It's time for a new chapter, a new functional group. New chapter, new functional group. And that new chapter is quite interesting. In this new chapter, I'll teach you about things that smell good, I'll teach you about chemicals that for many years, there were wars about over those chemicals. And what is that new chapter? Well, I'm going to have to open it up first. All right, thumbs up, people. Everybody see aromatic compounds on their screen? Thank you. All right, now, this new chapter is called aromatic compounds. Why are they called aromatic? Because they originally are organic compounds isolated, in other words, found in spices and herbs. An example of that is vanillin. By the way, Dr. White is a vanillin freak. I love vanilla in anything. And time for a quick side trip. I'll talk more about during the semester, but there's one in Evanston, there's one in Chicago. The best place around in the United States, one of the best, probably the best in Chicagoland, if not the United States, to get spices and herbs is a place called the Spice House. I've been a customer there for many years. If you go to your favorite search engine, mine is Google. You can either go to their store or, does everybody see the Spice House on their screen? I hope so. Thumbs up, people. You see Spice House? Thank you. And if I get rid of this, if I go here, all right, on your screen is my favorite vanilla extract. It's called Madagascar Pure Double Strength. Yes, it's twice as strong vanilla extract. If you look at the price, oh my goodness, is that expensive? It's worth every penny. An 8-ounce bottle, 8-ounce bottle is $82 to $83. 4 ounces, $42.50, almost 43. This stuff is the best of the best. And I usually buy the 8-ounce bottle. It lasts me a long time, but I love vanilla extract. I'll put it in things. I like it with a little sweetener and water. It's sort of a non-carbonated cream soda. Now, oh, I love it. This stuff is worth every penny of it. Now, they got a lot of other good stuff here. And if you haven't looked at their stuff, you should. Let's do one more that I like. That's I don't know. Can you see on the screen now the brown chipotle chilies? I usually get it in the bag because I already got one bottle I can refill. This is the best. Oh, I love this stuff. It's got such a smoky flavor. They're cumin, and they have 3 different types of chili powder, which are all fabulous. The chili powder comes as regular, hot, and really hot. I think they call it medium hot. The really hot is just too hot for me. When you put it in a dish to get also chili, and I use the medium hot. That gives a nice kick to it. And they have another one. Everybody see the ground habanero chilies? This stuff is dangerous, dangerously good, but it's hot. I mean, super hot. You got to be real careful with it. And later in the semester, I'll talk to you about a story with this and tell you about them. Probably one of the most stupidest things I ever did in my life. Yes, I can do stupid things too. So aromatic compounds come from different herbs and spices. They have unusual chemical properties, especially their stability. They don't change over time. They don't go bad. And many of them have a ring that has 6 carbons and 6 hydrogens. And that's an aromatic compound. Now, thinking about it, I talked about how many uh, wars have been fought over aromatic compounds. And there's a really great book, which is about time for me to read again. Really great books in my life. I reread every couple of years because they're just great books, like old friends to visit. And everybody see on the screen from Amazon, and I don't get any kickback, Napoleon's Buttons and how 17 molecules changed history. This is a great book. The reason it's called Napoleon's Buttons is, and I don't know if it's true or not, this could be sort of, I don't know if you call it a wife's tale or whatever, but why did Napoleon's army lose in the winter in Russia? Well, one thing this book talks about is if their metal buttons in their uniform and their coats were made of cheap metal in the cold winter in Russia, they became very brittle in the cold weather and broke. If you can't close your coat or keep your pants buttoned in the weather, it's going to be hard to fight. And that's one reason. Is that true or not? I don't know. But two more rings and we'll stop. One more ring. I don't shut off the phone because once in a while I might get an important phone call. This isn't, because I can look at the caller ID. But anyways, this talks about how wars were fought between the English, Dutch, French, and I believe Spanish over islands and areas of the world that made spices, which are aromatic compounds. Oh no, guess what? I just looked at the clock and we're done for today. I hope you all enjoyed our afternoon together, learning and practicing organic chemistry. But with that, I'm going to say, first of all, on Tuesday, since we finished it up, I'll go through the alkenes and alkynes problem set. On Tuesday, I'll go through the alkenes and alkynes problem set. Don't forget, the lab we did yesterday is due on Monday. And finally, I'm going to say, have a great rest of the weekend, because I won't see you until Monday. If you start having Dr. White withdrawals, you can always look at me on YouTube. Oh, that was awful. But anyways, with that, have a nice rest of the weekend. I'll see you on Monday. Gang gesund. Goodbye now.